Hey everyone, continuing for our exponential and polar form, we can talk about more properties regarding the argument and the modulus. And we start off with the conjugate. Alright, so the conjugate of a complex number would have the same modulus as the complex number itself. So z conjugate would have the same modulus as modulus z. Alright, because you can kind of really think of it this way. If z is a plus bi and z conjugate is a minus bi, you notice that the modulus is still square root a squared plus b squared. Alright, the argument of z conjugate is simply the negative of the argument of z. You can think of it through the Argand diagram, where if your complex number was here, you become the negative part for the conjugate, and there will therefore be a flip about the real axis. Similarly, if your complex number was in the second quadrant, and then you end up in the third quadrant, which is basically the reflection about the real axis. And hence your argument would then be measured from the anti-clockwise to clockwise, or from clockwise to anti-clockwise. So that's for z conjugate. Now we talk about z power n. For z power n, the modulus would be, well, following the normal modulus rules, mod z raised to the power of n. Alright, and you can actually see it with the exponential form, right? As I'll show you guys after showing the argument. For the argument of z power n, it is simply n times of the argument of z. Sort of like the logarithm property, as you'll see, arguments actually sort of like logarithm. Alright, so how is this a thing? Very simple. If we have REI theta raised to the power n, you notice that our modulus is now r power n mod z power n. Our argument, following indices law, ei and theta. Argument is now n theta. Alright, so that is for z power n. Moving on, we have zw. Alright, let's say z is of the form REI theta and w is of the form, let's say, kei phi. So we have the modulus of zw, again following modulus laws, mod z times mod w. The argument of zw is following logarithm law, arc z plus arc w. Why is that so? So we talked about, let's say, z becoming being REI theta and w being kei phi. Well, you notice that when you have zw, you'll get rk ei theta times ei phi, which will then give you ei theta plus phi. So that is it. That's why the argument is arc z plus arc w theta plus phi. Similarly, we talk about z divided by w. If you have z divided by w, again following modulus law, z mod z divided by w is simply mod z divided by mod w. Argument again follows logarithm law, arc z minus arc w. And you can prove it again with the indices, right? The exponential form. REI theta over kei phi, you get r over k as the modulus ei theta minus phi. So that's why you notice that the argument is simply arc z minus arc w theta minus phi. Now the last property, actually not really the last, but is when you, let's say, deal with a negative number. Alright, let's say minus kz. So what you want to do is, for the modulus minus kz is the same as modulus k then z. Alright, for the purpose of this, we will let k be a positive number. Alright, if k is a negative number, then honestly this is as good as mod k times z, right? The minus sign is quite obsolete. So for the purpose of that, we will let k be bigger than 0, so we then get rid of the modulus of k because we know that k is already positive. So mod minus kz becomes kz. The argument though would be actually following logarithm property as well. But you need to kind of be careful, because if k is a negative number, then you don't need to do this. All right. So only do this when k is positive. So what you do is simply split it to arc minus k plus arc z. We know that minus k is a negative real number. The argument is pi, then plus arc z. And then you can convert this to the principal range if you need to. Now, you need to do this conversion, especially with REI theta. If you have, let's say, minus 2 REI theta, where we know that theta is the principal range, R is positive, you need to change this, because we can't leave it or have the modulus being negative. So you need to change it to EI pi times 2 REI theta, and hence, as you can see, we have 2 REI pi plus theta. You notice that the argument is pi plus the argument of z. K is now 2, so we have 2 times R. And last but not least, why I put it 5.5 is actually not really 5.5. I'm going to put it as a separate one. When you have, let's say, modulus of a complex number being 1, there's a sort of a special property where, if you notice, we have modulus z equals to 1, we have EI theta. And if we have 1 over z, we have EI minus theta, which is z conjugate. So this is a very important identity that some questions like to test. And this is also kind of important when we look at, let's say, the half angle trick, where I will explain to you in the next video. All right, so some questions, they might purposely give you modulus 1, and this is the important property that they want you to use, where 1 over z, or z power minus 1, is actually the conjugate. All right, and this only works for modulus of 1. All right, so take note of this property. It can be very useful. Otherwise, I'll see you guys with the half angle trick in the next video.